Welcome to the course of SDN, Software Defined Networking. In lecture number 2, we are going to study the roadmap towards software defined networking. The key concepts that we are going to learn in this lecture are mentioned here. We are going to start by exploring the different types of network traffic that is in use today. Then we will see some demands for SDN or the technologies that actually leads to the development of SDN, and they are big data, cloud computing, and mobile traffic. After that, we are going to study two different types of requirements that are quality of service and quality of experience. Then we will see how routing happen in today's networks and how congestion control, what is congestion control and how it affect the transmission of information of packets in the network. And all these concepts are basically necessary for understanding software defined network and network function virtualization. The objective for today's lecture is that at the end of this lecture, you would be able to present an overview of the major categories of packet traffic on the internet. They are elastic and inelastic traffic. Then you would be able to discuss the traffic demands like the big data, cloud computing, and mobile traffic. You will also be able to explain the concept of quality of service and quality of experience. And also you will be able to understand the essential elements of routing. Finally, you will learn and understand effects of congestion and different types of techniques that are used for congestion control. Although we will not go into the details of congestion control mechanism, but you will be able to understand the basics of congestion control. And lastly, we will pave the ways toward SDN and NFV. Actually, these two topics are the discussion topics for discussion for the next week, but we will shed some light on these topics as well. So let us start with the different types of internet traffic or network traffic. Traffic on the internet and also on the enterprise network can be divided into two broad categories, and they are known as elastic traffic and inelastic traffic. First, let us see what an elastic traffic is. Actually, a type of traffic which can adjust itself to changes in delay or in throughput while still meeting the requirements or the needs of the user or application. Such type of traffic is known as elastic traffic. In simple words, you can say that any traffic that can adjust itself to the delay and throughput across the internet is known as elastic traffic. Delay actually plays an important role in the design and performance evaluation of any network. It is actually the latency for a bit of data to travel across the network from one endpoint to another endpoint. And there are different types of delays like processing delay, queuing delay, transmission delay, and propagation delay. On the other side, throughput is something that we measure how much data was transferred in a given time, or you can say how much packets arrived at destination successfully. It is normally measured in bits per second or sometime byte per second. There is a related concept which is known as bandwidth, and that is actually how much data could be transferred at any given time. That is the maximum available limit theoretically, but practically we never achieve that much bandwidth that is given for any type of network. Well, to summarize the elastic traffic, any type of traffic that would be able to adjust itself to the changes in delay or in throughput across the network, but still meeting the needs of the user or application. The traditional type of network or the traditional type of traffic that is actually supported on current TCP IP based networks is actually elastic traffic. And this is the type of traffic for which the internet were originally designed. You can see a large number of applications can actually generate such traffic, and they actually use the TCP or UDP protocol at the transport layer. Applications that actually use elastic traffic, they can be like FTP, file transfer protocol, or the secure version for FTP, SFTP. Similarly, the electronic mail protocol like SMTP, which stand for Simple Mail Transfer Protocol, for remote login like the Secure Shell Protocol, network management SNMP, which stand for Simple Network Management Protocol, or even your web access HTTP Hypertext Transfer Protocol or the secure version. They all are based on, or they all make use of the elastic traffic. They have different requirements, but we will not go into the details. On the other side, the second type of traffic on the internet is commonly known as inelastic traffic. And it is the opposite. Any type of traffic that does not easily adapt itself to the changes in delay and throughput across an internet is commonly referred as inelastic traffic. Example of such type of traffic include the multimedia transmission. There is the best example of inelastic traffic such as audio, video, or even high volume interactive traffic like the real-time applications. For example, simulation applications, like if you are going to train a pilot, then you would obviously use simulation at the beginning of the training. Okay, so all these are the type of traffic which actually relies on inelastic type. Okay, before going into the details of the cloud computing, the big data, and mobile traffic, which are actually the demand for the software defined network, let us see what it actually means. Consider the application areas that are actually generating stress on network resources and also on management. All these areas suggest that there is a burning need for using powerful tools like SDN, like network function virtualization. These concepts are new for you, but don't worry, with the passage of time, we will learn about SDN and NFV. But here it is important to note that why we need a new type of network architecture like SDN, like NFV. What were the burning need? What were the demands for such type of architectures? Actually, three things lead into the development of SDN. The first one is big data, the second one is cloud computing, and the third one is mobility. These areas suggest the need for using powerful tools like SDN and NFV. So if somebody asks you what are the burning needs, what were the demands for SDN, so there are other reasons as well. But the basic and most common reason are big data, cloud computing, and mobility. We are going to study them one by one. First, let us see what is big data. I remember a report by McKinsey, and they claim that the area of data science will be the #1 catalyst for economic growth of the industry. Nowadays, we are dealing with a growing torrent of data. The question is, where does data come from? Actually, the big data is generated by machines, it is generated by people as well as by organizations. Big data is a concept which actually enables an organization to create, to manipulate, to manage very large data sets, large volume of data. Data that we measure in terabytes, data that we measure in petabyte, in exabyte, and so on. And beside from that, it actually demands for the facilities in which such type of data could be stored, could be processed, could be analyzed, and the tools that are required for making sense out of this data. For that reason, distributed data centers, distributed data warehouses, cloud-based storage systems are common aspects of today enterprise network. Today enterprises that relies on such type of things. Data sets are continue to grow with more and more being gathered by like remote sensor, Internet of Things, smart cities, autonomous vehicles, artificial intelligence, virtual reality, augmented realities, your cameras, your smartphones, your microphones, online classes, etc., etc., etc. All these things are generating a huge amount of data. And if you see on the Google, go and search for it, how much data we are generating per second. How many videos are uploaded? How many videos are watched on YouTube per minute, per second? How much tweets happen per second or per minute? How many WhatsApp messages are sent and received throughout the world in 1 second? There are very useful statistics available on the Google. You can search for it. So big data is everywhere. Uh, for big data handling, we need some infrastructure. So here are the consideration. Traditionally, the business data storage and management technologies, which include like DBMSs, or if it is relational, then RDBMS, NES like network attached storage, SAN like uh, NES is for network attached storage, and storage area network. These are some terminologies which are related with the infrastructure, network based infrastructure, but we do not need to go into the details. But these are the technologies which are commonly used in traditional business setup, like the data warehouses and business intelligent analytic, which is an important part of any business. Actually, traditionally, or the traditional data warehouses and business analytic, business intelligent analytics systems, they are centralized within an enterprise infrastructure. Centralized mean central data repository within a database like RDBMS, and some high performance storage like NES, and networking facilities like SAN, and analytic facilities like BI. This is the traditional structure. Okay. However, increasingly, big data applications are becoming a source of competitive value for businesses, especially those that aspire to build data products and services to profit from the huge volume of data that they capture and that they store. There is every indication that the exploitation of data will become increasingly important to the enterprises in the years ahead or in the coming era. So big data is important, and it is going to change the way that currently our enterprises are storing the data, processing the data, managing the data, and analyzing the data. Here is an example of the big data networking. What you see here is actually different components. This is like a network ecosystem which is based on the big data. And in this figure, you can see different components. The key elements here are data warehouse that you can see at the bottom here. And data warehouse actually holds integrated data from multiple data sources, and it is used for data analytics and data reporting and stuff like that. We also have different types of servers, like we have data management servers, and we have like the network management server. They have different roles. For example, the data management server, they are commonly used for multiple purposes. Like they can run data analytic application, they can run your financial application, they can run your analytic tools, they can work as a sell of point and e-commerce web, things like that. While on the other side, the network management server, they are responsible for management of the network, for controlling of the network, and for monitoring of the network activities or operations. We also have some workstations here, or with the workstation, actually they are the system which are involved in the use of big data application inside the enterprise network. And then we also have the internet and other type of networks available. uh, for example, this enterprise setup can be connected with other enterprise data sources as well with the help of this internet, or even it can be connected with content delivery networks. Okay, and also it could be connected with IoT devices like different types of sensors, actuators, and other IoT input devices. So the important network devices which are not mentioned here, I think they are firewalls, intrusion detection systems, and like the IDS switches, routers. These things are not mentioned here because the focus is on the setup, the big data setup, and how the network ecosystem is for the big data. So this is an abstract level view of the big data networking ecosystem. Uh, Before going into the details of the second component, the second demand, which is cloud computing, let me tell you some of the characteristics of the big data. Big data is actually commonly characterized by using a number of V's. The three V's are very common, and they are like the first V is for volume, the second V is for velocity, and the third V is for variety of the data. Volume mean vast amount of data that is generated by different devices, by different human beings, by different machines, by different organizations every second. That is the huge volume of data. And on the other side, the second V stand for variety, which mean the different forms of data. Like we have the text data, we have the image data, we have the video data, we have the live streaming data, real-time data, and things like that. So that is actually the variety of the data. And we also have the velocity, the speed at which the data is generated. So these three V's actually contribute to the characteristic of the big data. With the passage of time, the number of V's are increasing. More V's have been introduced, like the veracity of the data and the valence of the data and things like that. So all these V's contribute to the big data characteristics. Okay, this was a bit about big data. The second demand is cloud computing, and we talked about cloud computing in our lecture number 1. And cloud computing, to further elaborate, let us consider a network model which was proposed by ITU, and it is shown in this figure. What you see here is actually an ecosystem which depict the use of the cloud computing for an enterprise setup. A cloud service provider, which could be any organization, actually they maintain one or more local, or you can say regional cloud infrastructure. And then you can see here we have like the intra cloud network, we have inter cloud network, two types of network, and we have two different type of OSS, which stand for operation support system. There are two categories. One is network, and the other, you can see here, the network OSS, and the other one is cloud OSS. Okay, so a cloud service provider, they will actually keep one or more local or regional cloud infrastructure. In this case, they have two infrastructure. They are local, they are actually distributed, and they are connected with the help of inter-cloud networks. An intra-cloud network actually connects the element of the infrastructure, and these element could be like the database servers, like the storage array, like other types of servers, for example, firewalls, load balancer, application devices, IDS, IPS, etc. And within the infrastructure, actually, the database server are organized as a cluster of virtual machine. So here you can zoom one of the virtual data center here. Actually, inside this virtual data structure, we have different types of virtual machine, and they are organized in the form of a cluster. So they are actually virtualization. We talked about virtualization a bit in the previous lecture. Like you have a single physical server, and on top of that we have multiple virtual servers, and multiple user can actually share a virtual machine, and that concept is known as multi-tenancy, which allow multiple user to share the same resources. Okay, so we talked about it in the previous lecture as well. Let us talk a bit about the network OSS and the cloud OSS. Network OSS is dedicated to providers. It is a system dedicated to providers of the services. It could be like ISP, like other telecommunication service who provide telecommunication services. They have to make use of the OSS. Actually, it includes services like which are related with the management and maintenance of the network, inventory of the network, configuration of the particular components, fault management, etc. Things that are related with the network. On the other side, the cloud OSS are dedicated to the providers of the cloud computing services. If you want to offer your services to the customer, then you have to make use of the cloud OSS, and it is used for maintenance, for monitoring, and for configuration of the cloud resources, and resources could be anything as we just mentioned. Okay, if you have different types of users, like a user can access the cloud services from laptop by using virtual private network, by using cellular networks, 3G, 4G, 5G, etc. It could be like a DSL setup, the network that you are using at your home, or it could be even by leased line. And in the previous lecture, one of the student elaborate a lot about these leased line that we are using in our country, and the two different types of leased line. One is from the US and the other one is from the Europe. Inside the enterprises, so you can access these cloud services from any of these devices. Okay. The third component is mobile traffic. And the basic idea is that we are shifting from our desktop computer and then from our notebook towards our mobile devices or our portable devices or like our smartphones. Because our latest devices, they have megabits, they provide you internet access at a high speed, and they give you opportunity to install different types of apps. They have different sensors, they have high megapixel digital cameras, they even have access to multiple types of wireless networks. For example, your smartphone has the capability to connect with a Wi-Fi network, with a 3G network, with a 4G network. They have the facility of Bluetooth, infrared, and plenty of other sensors are there. So plenty of onboard sensors are available. The devices are becoming more and more intelligent. Their battery life, which was a critical issue, it's improving over time. So all these things contribute to the data that we are actually generating by using these devices. The first rush, you can say, to wireless WAR was for voice traffic. As we saw in the previous lecture in the generation, the first generation was dedicated toward the voice market. Then the concept of the data, the internet, arrived. So if you compare the traffic generated by the mobile, we are actually shifting from voice toward data. You can see the growth of data. Normally we are using our cell phone more for data access, more for internet services rather than using them for calling. Okay, even if we want to make a call to someone, we use the data packet. We use different packages, internet packages. We use different applications like WhatsApp, like Skype, like Google Meet, etc. Okay, so there is a huge growth in the data traffic that we are generating from the mobile devices. Well, a big part of the mobile market is the wireless internet. Wireless users use the internet differently than fixed user, but in many ways, no less effectively. Wireless smartphones have limited displays and limited input capabilities compared with large devices like laptops and PC, but still mobile applications give quick access to the information without using websites and things like that with the help of application. Okay, and also the devices are aware of your location, and there is a famous saying that you do not need to search for information. The information is going to search you because of your location, because of your interest. They knows, our devices knows a lot about us as we know about ourselves. What we are doing, we are not aware, but the devices are aware of what we are doing, where we are, where we stay, how much long we stay there, which route we took, and things like that. Okay, I would prefer to skip this slide. This is not that much important. Now let us move toward the requirements of SDN. Now we are paving the ways towards the SDN. But before moving further, let us see the requirements. There are two basic requirements, or you can say two concepts that provide a way of quantifying the network performance that the enterprise desires to achieve. And they are the quality of service and quality of experience. And it enables the network manager to determine whether the network is meeting the user requirements, the user needs, and to distinguish the problem areas that actually require adjustment to network management, network traffic control, and things like that. So let us see what is quality of service, and then we will see what is quality of experience. Quality of service actually measurable thing. It is the measure. It is used to measure end-to-end performance properties of a network. And for that, we actually use service level agreement, which is known as SLA. And SLA is a document which is used between a user and the service provider. If you want to avail services of a service provider, you have to sign an SLA, service level agreement, and that is an important document which actually tell you about the quality of service. For example, in the SLA, it may be written that our services are available to the user 99.99% of the time. That is the quality of service. But more importantly, we have certain parameters that we can actually use to measure the quality of a service. Some of them are mentioned here, like the throughput, like the delay, packet jitter, error rate, and things like that. Throughput, as I just mentioned, is actually the bits or bytes per second for a given connection or traffic flow. How many packets are received at the receiver end? That is the throughput. Delay, we want the delay to be as minimum as possible. Okay, you can say that what is the average delay? It is also known as the latency. Packet jitter, on the other hand, is typically the maximum allowable jitter rate in a network. Jitter is actually a variation in the delay of received packets. At the sending side, packets are sent in a continuous stream. The space between the packet is equally distributed. But due to network congestion, improper queuing mechanism, configuration errors, other things can degrade the quality of the network, and hence due to this, delay between each packet can vary. The packet delay that you send at the receiver side could be different from the delay that we receive at the receiver side, and it is known as a packet jitter. We also have error rate. Several factors can contribute to error in communication. Typically, maximum error rate can occurs in wireless networks, and we also have packet losses. There is the how much packets will actually lost in the transmission, and also what is the priorities that you can assign to different types of traffics, and also the availability, which is very much important. It is expressed in as a percentage of time that the service will be available to the user. And also security is an important aspect. Different level or different types of security may be defined in the SLA document. So all these things actually guarantee the quality of service that you are availing from a service provider. Okay. Quality of service mechanism, in short, in summary, they actually ensure that business applications continue to receive the necessary performance guaranteed, even though they no longer run on dedicated hardware because you are availing services from somewhere from the cloud. Okay, but still certain quality of services must be there. On the other side, quality of experience is a subjective measure of the performance from the user point of view. It relies on human opinion. Quality of experience is important, particularly when we deal with multimedia application and multimedia content delivery. Quality of service actually processes uh, by the application themselves, they are not sufficient. Or you can say that the quality of service parameter, they are not sufficient for measuring the performance of the system. Why? Because users are not involved there. What is the user perception? What is the user perception of the service? What is the psychological effect on the service on the user? How the user actually interact with the service? These things are important, and it is the quality of experience which will answer these questions. For example, perceptual quality of the sensory aspect of the user experience. For video, for example, it could be like what is the brightness used in the video, the contrast used in the video. For audio, what is the quality of the voice, what is the clarity of the voice, things like that. Psychological is very much important. The user feelings about the experience. For example, is this service easy to use? Is there any enjoyable factors? What is the usefulness of the service? What is the quality? What is the satisfaction? Okay, is it put certain burden on the user while using the service? Psychological effects. And then interactiveness, which is related with the interaction between the user and the application or the device, such as what is the response time of the system. Okay, is the a given interface easy to use? Do we have support for physically or otherwise abled person? Are they able to access the technology or the solution or the application with ease of use or not? So quality of experience is something from which we guaranteed that our user satisfaction. You have to keep in mind the user satisfaction while developing a product and application or things like that. Okay, let's move forward towards routing. Routing is another important concept which is necessary for understanding the concept of SDN. We will not go into deep details of the routing because it itself is a big topic. But it is important to shed some light on routing as well as on congestion control or their mechanism. They are fundamental to the operation of a network and its capability to transmit. Actually, routing is about transmit or delivering packet. Okay. Some basic characteristic, or you can say the function, the primary function of the internet today is to accept the packets from the source and deliver them to the destination. That is the basic responsibility of the internet. is like different routes, different roads on which different vehicles are traveling all the time. That is the primary function of the internet, to accept packet and deliver them to the destination. And to accomplish this task, this objective, a path, or you can say a route through the network must be determined. Actually, more than one route are available is possible. Okay, the routing function is to determine which route to be selected for a particular type of traffic. The selection of a route is generally based on some performance criteria. The simplest one is to choose the minimum hop route. For example, if you want to go from city A to city B, then you have different options available. You can go either by taking an airline, you can go by taking a boat, by taking a train, by a bus, by your own car. Maybe if the destination is closed, you can go either by motorcycle or by bicycle or even by foot. Different options are available. Now, which option will you select? Your decision will actually depend on several factors. For example, the security, the time, the cost to reach to city B, uh, the congestion on the road, etc. Different factors can influence your decision. Same is the case with the routing. So one of the simple criteria to select the route is the minimum hop route. What is minimum hop? One that passes through the least number of nodes through the network to reach the destination. That is going to be the minimum hop. A generalization of this minimum hop is the least cost routing. A cost is associated with a link. Every link has a cost, for example, and this cost is important. In some cases, we want this cost to be as low as possible. In other, we want it to be as high as possible. To understand better, let us consider a network. These nodes are different devices, or different, you can say different computers, different routers, etc. And the links actually represent the path between the two devices, and these numbers actually represent the cost between each and every pair of devices or pair of nodes. Okay, consider an example. For example, this is an internet, and we want to send a packet from node number 1, which is represented by N1, to node number 6, which is represented by N6. So the shortest path in this case is going to be, if we want to use this criteria, the minimum hop, then that is going to be from N1 to N4, and then from N4 to and then N4 to N5, and then N5 to N6. Now if you see the cost here is 1, the cost here is 1, and the cost here is 2. The total cost is going to be 4. This is the best path in terms of you can say the least cost path. However, if your criteria is different, you are actually trying to give focus to the number of hops, then the best path is this one. The best route is this one. The less number of jumps from N1 to N3, and then from N3 to N6. The total number of hops here is 2. Okay, so you can select the best path by using different policies, and that is one of the function of the router. Actually, we will see now that a router can have different different components. One of them is the policy that it is actually using. So the cost associated with the links or assigned to the link, they actually support one or more design objective. For example, the cost could be inversely related to the data rate. That is, the higher the data rate on the link, the lower the assigned cost of the link. Okay, or it could be like the delay. It can represent the delay. In the first case, if we consider the cost to be the data rate, then the then the least cost route should provide the highest throughput. While in the second case, if we consider the numbers to show or to represent delay, then the least cost route should minimize delay. Okay, in routing, actually, as I just mentioned, the basic functionality is to receive the packet and then send the packet, forward the packet toward the destination. So here's an example of the routing forwarding tables. Sometimes we call them routing table, but the correct way is to use the word forwarding table. And that is the key function of any router, to accept incoming packets and forward them. And for this purpose, a router maintains forwarding tables. And these are some tables. Every node actually maintain a forwarding table. For example, this is the forwarding table for node 1, then for node 2, node 3. How these tables are created, we will not go into the details. But it contains some basic information. For example, what is the destination that is accessible, reachable from this node? And what is the next node to reach to that destination? For example, if you are at node number 1 and you want to go to, for example, if you want to go to node number 3, okay, so our destination in this case is node 3, then you will have to consult the node 1 table. What is your destination? The destination is 3. Which next node you will follow? The next node is 4, so you will reach there. Now you are at node number 4. You have to consult node 4 forwarding table now. You want to reach to node 3. Okay, the destination is 3. What is the next node? The next node is 5. So you have to go to 5. Now you are at node number 5. You have to consult this node forwarding table. Our destination is 3. And 3 is directly connected or directly reachable, accessible from this node. Okay. Now we arrived at our destination. So you see, actually we followed the forwarding table at each node. And this is actually a simplified example of how this might be implemented for the network. Okay. We also have a forwarding table for which is also known as the central forwarding table for the whole network, and we have forwarding table for each node. Okay. Next is that we actually have different types of routing protocol that we can implement to route our packets from source to destination. Each router make routing decisions, and that decision is based on knowledge of the topology of the network and also on the traffic or the delay in the network or the current condition of the network. To make such dynamic routing decisions, routers actually they exchange routing information with one another, and they do or they achieve such objective with the help of routing protocols. There are basically two categories of routing protocol. Routing protocol can be divided by using several approaches. One of the approach is based on autonomous system. According to this approach, we can divide the routing protocol into two categories. The first one is known as IRP and the second one is ERP. Or you can say interior router protocol and exterior routing or router protocol. Actually, we need to understand the concept of autonomous system. An autonomous system is a set of routers and other networks element that are managed by a single organization or that is under the control of a single organization. and it can consist of different routers, and they exchange information via common routing protocols and other decisions that are made inside the routers. So actually it is an autonomous system which is under the control of a single organization. Okay, a sharing a shared routing protocol, as you can see here uh, in the first category, which is interior routing protocol. Actually, it passes the routing information between the routers that are inside the same autonomous system. Or in simple word, you can say that the interior routing protocol, they are used within the autonomous system, and it does not need to be implemented outside that autonomous system. It is like inside your organization. It will connect the routers inside your organization, the other devices inside your organization, and it will be responsible for routing inside the organization. While on the other side, the exterior router or routing protocol (ERP), it is actually it is used to uh, to route the traffic between two different autonomous systems. The router in one autonomous system need to communicate with the router in another autonomous system. For that purpose, at least, we need another type of protocol which would be able to communicate or send the message or receive the messages from other autonomous system. And that protocol is known as exterior, as the name indicate, exterior routing protocol. Okay, it will enable, or it will be used to pass the routing information between routers in different autonomous system, not in the same autonomous system. Sometime the terms interior gateway protocol and exterior gateway protocol are also used to refer to the interior routing protocol and exterior routing protocol. So you can use either one of them. And here is the concept shown diagrammatically. Here you can see both type of or both categories of routing protocols. We have protocol inside the autonomous system, and we have protocols that actually make the communication between these two autonomous systems. The green colors, they actually represent interior routing protocol, and the pink color, they actually represent exterior routing protocol. Okay, this is the elements of a router. Consider it as a router. A router actually have many, or you can say a number of input output ports. What you see here, they are the ports, they represent the ports of the routers. These ports are used to connect different devices to the routers, like other routers or even system that can be connected to the routers. And you can see on each of this port, we have two different types of buffers. Packet arrives at the router port, and packet actually leaves at the router port. So for incoming packet, we have input buffer, and for outgoing packets, we have output buffer. These buffers are used to temporarily hold packets that are waiting for depart. As packet arrive, they are stored in the input buffer of the corresponding port. Beside, the router also examine each incoming packet, and then based on that examination, the router actually makes a routing decision. And for making that decision, the router consults the forwarding tables. Remember the forwarding table? It has the information about the destination, the next node, and how to reach there. Even it has the cost as well. Okay. Beside from that consultation of the forwarding tables, which is used to move the packet to the appropriate output buffer, packets queued for output, they are actually transmitted as rapidly as possible. And for that as the buffer is involved, so you know from operating system we have to use some sort of strategy like first in first out queue or other priority queues, etc. More commonly, a more complex queuing discipline is used, but to make things simple, for example, consider that we are using FIFO, first in first out. So the packet that arrive first will leave this buffer first. Okay, beside from forwarding table, beside from ports, beside from input output buffers, we also have some routing policies, which is shown here. Okay, a policy may also influence the construction of this forwarding table and how various packets are treated. Policies may determine routing not just on the destination address but other factors like what is the source address, what is the size of the packet, and what is the protocol payload. Payload is actually the data that we are adding to the at each layer, but we will not go into the details. Okay, so this is about the elements of a router and how it functions or how it works. Finally, let us see about congestion control. If the traffic demand on uh, on an internet, for example, exceed the capacity, the current capacity, or if the internet does not manage the traffic efficiently, what will happen? Congestion will happen. If I'm delivering my information too quickly, then you would not be able to capture all the information. What will happen? Congestion. The effects of congestion are very dangerous in the networks. If packets arrive too fast for a router, for example, to process them, okay, because router need to make routing decision. If the packet arrive too fast, then what will happen? Or if, for example, the packets that are at the buffer and the buffer is not clear very fast, then what will happen? Eventually packets will arrive, the buffer is full and there is no memory available, then what will happen? A saturation point will reach, okay, and then incoming packets would be lost. Effect of congestion, very dangerous. We have no room for incoming packets, eventually packet will lost. Okay, so we need to handle this congestion. Two strategies are normally used for this purpose. The first strategy is to discard any incoming packet for which there is no room available. This is a very simple strategy but not very efficient strategy, because you are dropping the packets, and what is going to be the effect? The sender is going to resend the packet, and this way we are creating sometime more congestion on the network. The second strategy is that node that is experiencing congestion or the problem of congestion or some sort, you can introduce some sort of flow control mechanism on that node in order to deal with the incoming traffic. Okay, for that purpose you can see in this picture, it illustrates that each node's neighbor is also managing a number of queues. For example, node number 6, input queue is there at this node. If the flow of packet from node 5 is very fast, then it will cause the output buffer in node 5 to send packets to node 6, and the node 6 queue will fill up. Thus congestion at one point in the network will happen, and this will propagate throughput a region or the entire network. Although flow control is indeed a powerful tool, you need to use in such a way as to manage the traffic on the entire network, not only on that node. Okay, to summarize the congestion control, actually we need to study some graphs. These graphs are ideal graph. In the practical situation is different from this ideal situation, but It is important to understand because it helps us to understand the real situation. So the top most graph here, actually it shows a steady state uh, total throughput, and throughput is the number of packets delivered to the destination through the network. And actually we are considering two things, load and throughput. So as you can see, the load on the network is increasing, but still the throughput is increasing. Both are like a steady state. Load is increasing, but the throughput is also increasing up to a certain point, and the value here is 1.0, for example, at a higher input load. However, what will happen to the end-to-end delay experienced by the average packet even with this assumption of ideal performance? Up to this point, okay, the throughput is okay, but after this point, throughput is not increasing further. At negligible load, there is some small constant amount of uh, performance, but after that, the performance is actually not increasing. On the other side, if you see the delay, the load is increasing, but you can see the delay is not that much, like a negligible, or you can say constant amount of delay is here. And it consists of maybe the propagation delay, which is a type of delay through the network from source to destination, plus maybe it is a processing delay at each node. However, the load on the network increases with the passage of time. What will happen? Then the queuing delay at each node are needed they are also added to the processing delay and to the propagation delay. Now, when the queuing delay is added to this load, then there is a rapid increase in delay of the network. And the reason for this increase in delay, even when the total network capacity is not exceeded from 1.0, still we saw a large amount of delay in the network is because of the variability in load at each node, because the buffers that we are using at each node, they do not have infinite capability, they have limited memory. Okay, so that is why the delay effect is more dangerous. Okay, and this happen when a burst of packets arrive at a node. For example, it will take some time to clear the backlog. Okay, and it is important to grasp the meaning from this figure before going into the next slide, that this figure actually represent the ideal situation. Okay, but our real situation, our practical situation is like this. This is the real situation, not the ideal case. And here you can see that now we have infinite buffers at our nodes, at our routers. Okay, and they can be full with the incoming packets, and congestion can occur. So in practical, buffers are finite and they lead to buffer overflow and congestion occur in the network. So consider what happens in a network with a finite buffer if no attempt is made to control congestion. Let's suppose congestion occur in our network. Okay, so here it is. We have two parameters, load and normalized throughput. So we have three states now: no congestion, moderate congestion, and severe congestion. At light load, throughput and network utilization increases. You can see here, load increase, throughput increase, network utilization, performance increase. As the offer load increases, the utilization and the throughput also increases. As the load continue to increase, a point is reached, and that point is represented by A. Beyond this point, the throughput of the network still increase. but at a rate which is slower than the rate at which the offer load increase. It's like this: you are attending a class, the lecture is delivered by the teacher, so you are gaining all the points. With the passage of time, your understanding become more meaningful, more productive. But after some time, for example, let's suppose after 30 minutes, your interest in the class is still there, but it decreases. Okay, and then a second point will reach, which is represented by B here. After this point, what will happen? The load increase, but the throughput will not increase. Instead, it will goes down. So this is the point where the teacher need to stop the lecture, or he or she need to introduce some ice breaking activity. So as the load on the network continues to increase, the queue length of various nodes continue to grow, and a point B is reached, beyond which the throughput actually drops with increased load. The reason for this is that the buffer at each node are of finite size. When the buffer at the node become full, the node must discard the packets. And what will happen when the node discard packet? The source retransmit the packets. In addition to the new packets, they are actually retransmitting the old packet that were discarded by the nodes, and it will actually create extra load. Okay, so the throughput is not increasing but rather decreasing. And same is the case for delay, but you can study this graph as we are getting late. Okay, now we have reached to SDN and NFS after reading these concepts, after understanding these concepts. Well, with the ever increasing volume and variety of network traffic, which is generated by such high demand sources like big data, like cloud computing, like mobile traffic, etc., it become increasingly difficult to meet the quality of service and quality of experience requirements of the user. Networks need to be more adaptable, more scalable, more manageable, and more controllable. To provide adaptability, scalability, controllability, and easy management, two key technologies that are rapidly being deployed by a variety of network service provider and application providers, they are known as SDN and NFV. Software defined network. It is like a tipping point at which it is replacing the traditional networking model. Although it is not completely replaced, but it is moving forward to replace the traditional networking model. It actually provides an enhanced level of flexibility, customization, adaptability, scalability, and things like that. Why? Because it is there to meet the needs of the new networking and IT trends, like the need of the cloud computing, the need of the edge computing, the need of the fog computing, the need of mobility, the need of social networking, the need of video streaming, the need of augmented reality, the need of virtual reality, the need of flying area network, vehicular area network, and things like that. Now, SDN, how it is, or what is the functionality? Actually, we will go into the detail of SDN in our coming lecture, but two elements are actually involved in forwarding packets. Now, if I use the word forwarding table, you have to know what I means. I'm referring to the devices that actually forward the packets, and they have forwarding tables, and they have certain policies, and they use certain rules, certain algorithms for doing that. Actually, the routers, they have control plane and data planes. Prior to SDN, the control function and the data function, they were integrated at each networking device. Like every router, every bridge, every switch, and so on, they have the control plane as well as the data plane, but they are combined in each and every device. Control in such traditional network is exercised by means of a routing and control network protocol that is implemented in each network node. This approach is inflexible and it requires all the network nodes to implement the same protocols in order to communicate with one another, to pass packets to one another. However, with SDN, a central controller performs all the complex tasks. As you can see, we actually separate the control plane from the data plane. And that is the whole logic of SDN. In the traditional networking devices, the control plane and the data plane, they are combined in each and every device. While in SDN, we actually separate them. And the control plane is handled by several SDN controller, while the data plane is as usual. Okay, so we will see more about SDN in the coming lecture. Actually, the SDN control plane will consist of one or more SDN controller, as you can see here. And well, we will go into the detail in next lecture. I'm not interested to make all the thing about SDN in this lecture. And the second technology, the second driving force is known as NFV. A key driving factor in the development or in the deployment of SDN is the need to provide flexible network responses to the widespread use of virtualized server. You know, virtual machines that we just studied in the cloud computing environment, they play an important role. So virtual machine technology over the internet or an enterprise network has until recently, it has been used for application level server functions such as database servers, cloud server, web server, email server, and so on. The technology was initially used at application level, but now the same technology can equally be applied to network devices. That is the main point. The application level server functions, now it could be applied to the network devices like routers, like LAN switches, like firewall, like IDS, like IPS servers. How? Here is the whole story. You have different network devices like switches, like routers, like firewalls, like IDS servers, intrusion detection system, etc. And then you can map them into a virtualized platform. So NFV actually decouples the network functions like routing, like firewalling, like intrusion detection, like network address translations, etc. It separates them from the proprietary hardware platforms and then implement these functions in software. This is where the software part comes in. Okay, so you actually separating the functionalities from the hardware and you are deploying them, implementing them in software. NFV has a number of features in common with SDN because in SDN the S is for software, and here we are actually focusing on the software as well. So you can say they actually share common objectives, like they use standardized application programming interface, which is known as APIs, and both move functionalities to the software. That is another common objective. They actually use the commodity hardware platforms instead of proprietary platforms, and they actually support more efficient evolution, deployment, scalability, and things like that. So they have different things in common. So NFV and SDN, they are actually independent but complementary scheme. SDN decouples the data and the control planes of the network traffic control, making the control and routing of network traffic more flexible and efficient. While on the other side, the NFV decouple network function from specific hardware platforms with the help of virtualization to make the provision of these functions more efficient and more flexible. Okay, so we will shed more light on these two topics in the coming lecture. Thank you so much for watching this video. Take care and goodbye.